Welcome back, everybody. I'm your host, Peter Duveen, and we're moving on to part 2 of circular motion. I've decided to use the same diagram because it looks like it's in pretty good shape, so there's no reason really to change it. But now we're going to try and measure the magnitude of the acceleration. That is, the rate at which the velocity is changing in the direction in which the acceleration is acting. Now, in our previous presentation, we established that the direction of the acceleration is toward the center of the circle, and that the magnitude of the acceleration is uniform. So, we're going to be a little bit clever here today. And we're going to use some very simple mathematics and simple geometry to coax out of this situation the actual magnitude of the acceleration. And this is how we're going to do it. We're going to use the famous Pythagorean theorem. I'm going to extend this line up this direction, and I'm going to extend this tangent line moving through the initial position of my body through that direction. To make this a little bit bigger so we know there's a body there. And I'm going to do something very interesting here. This is the initial position of the body, and this is the position of the body at time t. Is moved over here. I'm going to erase this here and skip that. And what I'm going to do is, I'm going to assume first that the body moves in a direction tangent to the circle at its velocity v. Therefore, the distance it will move during this time t is vt. At the same time, I'm going to let that body, I guess once it gets there, or actually during the process, I'm going to let it fall in the direction of the radius here. And we're assuming that the acceleration is a. Acceleration equals a. And we know that when something is moving at uniform acceleration in a particular direction, that the distance it falls is equal to 1/2 a t squared. So the point being this, that I'm going to let the body both move at the velocity times the time to this position, and at the same time I'm going to let the acceleration act at to generate a distance such that it will just go right back to the circle, which is where it's supposed to remain. So by the composition of these two displacements, one generated by the acceleration, one generated by the velocity, we will have had it to move right back to the position that it will be in if it's moving in circular motion. Now, what I'm going to do, because you can see that there's some questions that one might ask about this, how is the body actually traveling during its transfer from here to here? Well, I'm going to assume that this expression becomes more and more accurate as we get closer and closer to the beginning of the motion. Now, I can just erase some of these for a moment. This, and let's use our Pythagorean theorem. This is the radius of the circle here, and this is also the radius of the circle. So I'm just going to set up the Pythagorean theorem the way it is usually done. The square of the legs is equal to the square of the hypotenuse. The sum of the squares of the legs is equal to the square of the hypotenuse. So here I have r squared plus the velocity times the time squared, which means that's the whole expression squared. So that would be the velocity squared times time squared, actually. Is equal to this whole distance squared, which is r plus 1/2 at squared. That's this distance. R is this distance. Is equal to r plus 1/2 at squared. Excuse my handwriting. And we're going to square that whole thing, that whole distance. Okay. So our main task here is to look at this expression, r squared plus b squared t squared is equal to. Now, if I square this, if I multiply this expression by itself, I will get r squared plus 2 times 1/2 at squared. Oops, is that right? Times r plus. Now I have to square this piece, and it's just going to be 1/4 a squared t to the 4th. And square the whole thing. Then I'm going to subtract r squared. You notice there's an r squared here and an r squared here. So I'm going to subtract those r squared, and I'm just going to be left with b squared t squared is equal to, these two cancel, so I'm just left with a t squared plus, oh, got something there. Got to put a little r in there. A t squared r plus 1/4 a squared t to the 4th. And now finally, I'm going to do something pretty sneaky. I'm going to divide both sides by t squared, which means I'll have to divide this expression by t squared and divide this expression by t squared. Here the t squareds cancel out, and I'm just left with b squared is equal to a r plus 1/4 a squared. Now, t to the 4th divided by t squared is simply t squared. Okay, now remember, you want to take this closer and closer to the very beginning of our motion, just as our motion starts out. And just as our motion starts out, notice that this expression here is not dependent on the time. In other words, this term of the right side of our equation is not dependent on the time, but this is. And notice as we get, as t is smaller and smaller, this expression, this entire expression becomes smaller and smaller, unless a, of course, was infinite, which it is not, is some fixed amount. So, therefore, as we go to the very beginning of our motion, this part of the expression virtually becomes 0, and we're just left with b squared is equal to acceleration times the radius. Or, if you divide both sides by the radius, you have v squared over a is equal to r. Oops, my mistake. That's not what I wanted to say. I wanted to bring the r down here. V squared over r is equal to a. So here we have a quantitative expression for the acceleration in terms of the velocity, or you might say this in terms of the speed of the body, and in terms of the radius of the circle. If we double the speed, we're going to quadruple the acceleration, and if we triple the speed, we're going to the acceleration will increase by 9 times, because the acceleration increases as the square of the velocity. Whereas if we double the radius for the same velocity, we're going to actually have the acceleration. So we can look at this expression and analyze it, and this is a very important formula, you might say, or it's rather an important formula, and it's a rather substantial result that we've achieved during this lecture. So thank you for listening.